All right, subscribers, welcome back to another episode of Science with Surback. Today we take a deeper look into our unit on electrochem, and we're going to focus on section 20.4. Now, before we get going into the details of these notes, there are a few objectives that I would like you to meet by the end of this video. Objective number 1, given appropriate standard reduction potentials, calculate the cell potential generated by a voltaic cell at standard conditions. Objective number 2, use standard reduction potentials to predict whether a reaction will be spontaneous at standard state conditions. Okay, so we start out here with just some basic definitions that are associated with this business of electrochemistry. And the last set of notes, I left off with drawing the picture and outlining the diagram of a voltaic cell. And I said, hey, this particular cell would produce 1.07 volts. Well, how we got to that point is this information here. So we get underway here with the cell potential, which is defined as the force required to push electrons through the external circuit. So basically, it is measuring the force that these electrons are moving through that wire in that voltaic cell. Now, we abbreviate cell potential as a capital E and a subscript cell, and that is the electromotive force of a cell, or the EMF. Now, I'm not going to get into a whole lot more details besides, hey, that is what it stands for. Now, if we pause and we kind of do a physics perspective on this potential difference, you can think of this as moving electrons. Specifically, it's the difference in electrical potential. And we measure that in volts. And again, the difference between potential would be those substances in our voltaic cell. Now, a very important concept to remember, or a very important conversion to have in mind, is that 1 volt is equal to 1 joule per coulomb. Okay? So that may be a helpful conversion as we go down the road further in this particular unit. Now, the other thing that we have to remember is this. Electrons in a spontaneous process flow from an anode to a cathode. So remember, the anode, that is where the oxidation occurs, and the cathode, that is where the reduction occurs. So anode, remember, negative, to the cathode, that is positive. Okay, so that's something that we have to keep in mind. The other thing that is very important is that the cell potential is greater than 0 for a spontaneous reaction. So in other words, that's saying, hey, we're going to have a positive number for a spontaneous reaction. And this is really important as we start to do some problems. And the other thing, we've mentioned it before, but we have these standard conditions. So initially here, all solutions of the voltaic cell are 1 molar solution at 1 atmosphere of pressure at 25 degrees Celsius. That allows us to use these charts in our problems, and I'll show you those charts here in a couple of moments. Now, again, because we're under standard conditions, we have what looks like the degree sign here, and that's just saying, hey, this cell potential is under these standard conditions, and again, that allows us to utilize our charts that we have in our periodic table packets. Okay, so we went over a lot of details here, and there's a lot of information here to take in, and there's things that we will utilize throughout our use of problems, or throughout our use of solving problems during this entire unit. So let's move on here of how exactly do we get these cell potentials. So the way in which we get these cell potentials is through this standard reduction potential. Now, what's really important for us is that we are going to get numbers or values in our chart, and we have to keep those numbers and values the same as what is listed in the chart, okay? Now, particularly here, the standard reduction potential here is just defined as the cathode minus the anode in our standard cell conditions. Now this is measured in volts, and we'll see this here on our chart here in just a second. The other thing that I want to point out here is, how did we get these values? Where did we get these numbers that I'm about ready to show you in this chart? Well, the way in which they compared all of these items to a particular voltage is they used the standard hydrogen electrode. And so the standard hydrogen electrode is defined as the reduction of H plus to hydrogen gas under standard conditions of an electrode. Okay. Now, the important part here is that this reduction here, this reduction is equal to 0. Now, you can see in this picture of how we have this set up, where the hydrogen, the standard hydrogen electrode, produces that voltage of 0. So what we see out here read out in our voltmeter here is exactly the voltage that this, our oxidation, is occurring at. And that's how we got these charts, or how we got these values. So you can see that, yes, if you look closely, it is 0.76. But more importantly, I want to use this chart that I have provided in notes. Now, what we have here is this. We have zinc 2 plus 2 electrons yields solid zinc, and that gives us our standard cell potential in volts of negative 0.76. And I'm going to write that down and talk about it here momentarily, okay? And I want to point out this, that yes, our standard cell potential here of our zinc that's being reduced reads out as 0.76, but on the chart it's negative 0.76 volts. Okay, so why may you ask, why is this a negative 0.76 volts, but here on the value here on the voltmeter, it is 0.76. And I'm going to write this a little bit cleaner so that it's a little bit easier to see. So I'm going to write this as negative 0.76 volts. Okay, and so now we get to explaining why this is negative and why this is positive. So our reasoning for this is as follows. Notice here on our chart that it says standard reduction potentials. So when we find our values here, these are reduction reactions here, okay? So in our chart, these are reduction reactions. And now I want to talk a little bit here about the sign of our standard cell potential. So if we have a negative cell potential there, that is a non-spontaneous process, okay? And if we have a positive, that reduction here is a spontaneous process. Now, this still hasn't answered the question of, okay, yeah, I have a negative value here, but overall in my voltmeter, it's reading out as a positive 0.76. Well, let me write this down here, and I'll answer this momentarily. All right, so how we get to this point here of the voltmeter reading out 0.76 is as follows. Notice here, if you take a look at the picture, that the zinc is the anode. And that's because this particular reaction is an oxidation reaction. And I'm going to box that in red so we can identify this. This is the oxidation reaction, which means that this is going to be our anode. Now, if this is the oxidation reaction, our hydrogen, our H plus here, is getting reduced, okay? So I'll box this here in green, and I'm going to box the whole thing in. This is our reduction reaction, which means that this is our cathode. Now, you may be wondering, okay, yeah, how does that answer my positive versus negative point here? Well, if I plug these values into my equation, you'll see why here. So I'm going to rewrite the equation of the overall cell potential of what we have listed here is equal to the cell potential of the cathode minus the cell potential of the anode. All right, so I'm just going to plug my numbers in here. And so the cell potential of the cathode is listed at 0 volts, okay? So 0 volts minus the cell potential of the zinc is listed at negative 0.76. Again, negative 0.76 volts. And something that I want to point out, you write down, if we're using this equation right here, you write down exactly what is seen in the chart. If you flip the signs and you start working with that, you're going to mess up the equation, and you're not going to be able to calculate the standard cell potential of the overall voltaic cell correctly. So keep the signs exactly as they are listed in your standard reduction potential tables. Now, if you do that, 0 minus a negative 0.76, that is where we get the positive 0.76 volts equal to our standard cell potential of the overall reaction with the oxidation of zinc to zinc 2 plus using that standard hydrogen potential. So again, we're going to see this cathode minus anode. The big thing is identifying what is the oxidation half reaction, what is the reduction half reaction, because that will ultimately tell us the cathode and anode. And hey, once you have these values in there, then you can move right along. Now, I'm going to point something out too before we move on to our next page of notes here, and that is this. So you have this standard potential table that I've provided in notes, and I want to point out this. Cr2O7 2 minus plus the 14H plus 6 electrons yields 2 Cr3 pluses plus 7 waters. On your periodic table packet, there is a mistake. And if you notice this one right here, it says Cr07 2 minus. That is a mistake on your packet. And so I want you to put a little subscript 2, because that will play a role into what we have here. Again, that should be Cr2O7 2 minus. That will help us out going forward, okay? So keep these two charts handy, both your periodic table packet and your standard reduction potential, as we go through some examples, okay? So let's go through some examples here. All right, so we've seen this, or we've drawn this in our voltaic cell. And so it says we have solid zinc plus the copper 2 plus yields zinc 2 plus plus your solid copper. And the overall cell potential is 1.10 volts. Given this information here that zinc reduced to solid zinc is negative 0.76 volts. We want to calculate the cell potential just for copper getting reduced to Cu. Okay, and so now you may be wondering, okay, what do we need to do? Well, in these types of equations, whenever we're using our cell potential, we always start with our formula. So the cell potential of the overall cell is equal to the cell potential here, cell potential of our cathode minus the cell potential of our anode. So what we need to do, keywords cathode and anode, what we need to do is we need to figure out what gets reduced and what gets oxidized. So what we need to do is this. We need to take a look at our charges, okay? So zinc, we start out here in our reaction. Zinc is in its solid state, so it has a charge of 0, or more appropriately, an oxidation number of 0, okay? Copper, you can see here, has a 2+ charge, so that makes our oxidation number positive 2. And then over here, zinc is a positive 2 now, and copper is in that solid state, so it has a oxidation number of 0. Now, zinc goes from 0 to 2+. It has lost electrons, okay? So right here, I'm going to write this underneath here. Zinc has lost electrons. That means it is oxidized. And I'm going to call this the oxidation reaction. And that is because zinc lost electrons. So we went from solid zinc to zinc 2+. And I want to add this. We need to add those electrons into that. Okay, so if zinc is oxidized, then that must mean that copper is reduced. So I'm going to put reduction reaction. Okay, so reduction reactions, Cu2+ is going to go to solid copper. And now the electrons in this case here, need to go on that left-hand side. Let me rewrite that so it looks a little bit cleaner. And so that's great that we've identified that. Now the important part for us is this. The oxidation is our anode. So I'm going to put this as, hey, this is the anode in our particular reaction. Down here, the reduction reaction is our cathode, okay? So this is our cathode. It told us that the standard reduction potential for zinc to solid zinc is negative 0.76. So when we go to list things out here, and we can do that in our formula, we already know what the anode is. The standard cell potential is also given in this problem as 1.10 volts. So what we are looking for then is going to be the standard cell potential of the cathode. And again, it is given in the chart as negative 0.76 volts. Just because we flipped our products and reactants here, we do not change this value in our chart if we are going to use this particular formula, okay? Now, we're going to plug some numbers in, so we get 1.10 volts, equals the standard cell potential of the cathode. We don't know that. That's our whole goal here. And so we are going to find that out minus the negative 0.76 volts, okay? And so remember, negative minus a negative, or excuse me, minus a negative is a positive. So what you actually need to do here is subtract 0.76 volts from each side, okay? So I'm going to get my calculator, and we're going to take 1.10 minus 0.76 volts. And again, that's because a minus or a negative minus a minus a negative is a positive. That's why we subtract 0.76 volts. So when we do that here, we take 1.10 minus 0.76, and we get 0.34 volts. So our standard cell potential of our cathode here is 0.34 volts, and it is a positive. Now, more importantly here, let's answer this question up here. So if we had the reduction of copper 2 plus to solid copper, we would get a cell potential here. We would get a cell potential of positive 0.34 volts. Okay, let me clean that up a little bit here. Again, that would be a positive cell potential of 0.34 volts. All right. So that is how we would go about utilizing our formula to solve these problems. Now, you could have read, hey, this is the reduction, so I'm going to solve for the cathode, but I wanted to show you this particular process. All right. So this would be our answer for this particular problem. All right, so we are now going to go a little bit more into depth, into detail here with our equation of our standard cell potential. All right, so the next problem here does not get into as much detail telling you what is reduced or what is oxidized. That's our job, that we have to go find this here. So it says, hey, use the standard reduction tables to calculate the voltaic cell described below, which uses this particular reaction. Now, there is a lot going on here, and so the best thing that you can do is you can identify what is reduced and what is oxidized here. Okay, so what we'll do here, the easiest thing to start with is this 6I minus. Again, what's nice about the ion here is it tells you the charge. Now we are interested in the oxidation number of just one of those ions or one of those elements here. So I'm going to put out here to the side the oxidation number. Okay. So for I1 minus, it is a -1. Now, we go over here and we find our iodine again, and I2, that is in its natural state. So remember, any element in its natural state has an oxidation number of 0. Now, okay, we went from a -1 to a 0. That means it lost electrons. So I'm going to do this. I'm going to say our oxidation reaction is as follows. It is our 6I minus getting oxidized to our 3 I2s, and we cannot forget about our electrons. Okay, now I'm going to leave a little space. We're going to get back to this. This means that our Cr2O7 is going to be our reduction reaction. But I want to show you the oxidation numbers of how we get to this point. So we'll start out here with our Cr3+. Again, the charge here indicated by the charge on the ion is the oxidation number. So that's a +3. And then we get to this over here. Now, with our Cr2O7 2-, it is a polyatomic ion. So the way in which we solve the oxidation number for Cr is as follows. Again, we don't know the oxidation number of Cr, and we also have two of them. So you can think of this as Cr times 2 plus, and I'm going to put this in parentheses, plus oxygens. Oxygen's normal oxidation number when it's involved in a compound is -2. And we've seen that utilizing the periodic table. There's a few exceptions when oxygen is not -2, but we can look back and go through those rules. Now, we multiply that charge by the number of oxygens present, which is 7. And for a polyatomic ion, you set this whole equation equal to the overall negative charge. Okay? So I'm going to simplify here. I'm going to have 2 Crs plus a -14 equals -2. And once more, I'm going to simplify by adding 14 to both sides. So if I add 14 to both sides, I would get 2 Cr. Let me write that correctly. 2 Cr equals a +12. Okay? Now, we divide by 2 because we have 2 Crs. So that means the charge for each individual Cr is a +6. So Cr has a +6. So it went from a +6 to a +3. That means it gains electrons. Reduction is gain of electrons. So we can confirm our assumption here that the reduction reaction is going to be involving Cr2O7 2- and our Cr3+. And I want to give a little space on both sides of this equation, and I'll tell you why here in a moment. All right, so remember when we balance via half reactions. Remember we had to balance oxygens. You can see right now our oxygens are not balanced. So what that means is we have to involve H+ and we have to involve waters. So if you see here in our overall equation that H+ is here and our water is also here in this equation, that is because we're trying to balance those oxygens, and we balance via half reactions. So on my left-hand side, I'm going to put my 14 H+, and on my right-hand side, I'm going to put my 7 H2Os. Okay? And our last thing here is this. I want to find our standard reduction potentials for each of these reactions. Okay? So I'm going to start out here with this, our I- and I2. So I'm going to use the table I provided in notes. You're more than welcome to use the periodic table packet. It's embedded within that. But we'll find our same results, or we should find our same results here. All right, so now I go down to this. All right, so I have I2 plus 2 electrons is yielding 2 I-. Well, this is a very similar reaction, okay? And so I am going to note this. Number one, I'm going to write that cell potential. And even though it's flipped, remember, we write the value of the chart. So this cell potential here for our oxidation half reaction is, if you look closely, it is positive 0.45 volts. Now, you may be wondering, hey, okay, well, here it said I2 plus 2 electrons yields 2I minus. Well, that brings me to a very important point here, and I'll write this down in blue, all right? So I'm going to draw an arrow. I'm going to draw an arrow to each of these coefficients, okay? And so I'm going to put down this, or I'll say this and then I'll put it down. Our standard reduction potentials are our intensive properties. So what that means for us is as follows. We could have here, and I'm just going to put a 1 for our example, our iodine getting reduced to 2I minus, and it is going to have a standard cell potential of 0.54, a positive 0.54. Now, because it is an intensive property, that means it does not matter how much we have. So if we do this, if we say we multiply everything by 3, that does not mean that we multiply our value by 3. Our standard cell potential is still going to be 0.54. So no matter what you multiply your coefficients, it does not multiply your standard cell potential. So even though we have 6 I minuses and we only have 2 I minuses, that does not mean we need to multiply that standard cell potential by that value. It is going to stay the same, and that is what this is saying. Okay, so now we can get to our final problem here, or actually solving for the standard reduction or the cell potential here. So I am going to label a few things, and that is, one more thing. We need to find the standard cell potential for our chromium. So our Cr2 O7 2 minus plus 14 H pluses plus 6 electrons, which we need to add these 6 electrons here. And so I will add these 6 electrons. What this gets us here is as follows, okay? It gets us a value of positive 0.133 volts. So our standard cell potential here is a positive 1.33 volts. Okay, now comes the very, very important cell. The oxidation reaction is our anode. So I'm going to box this in red here. I'm going to box this in red. And this right here in red, this is our anode. Okay, now in green, I'm going to box in here. Our reduction reaction is the location for the cathode, all right? Now, this is going to make life easy when we plug it into our formula. And remember, our formula is as follows. The cell potential, the overall cell potential, is equal to the cell potential of the cathode minus the cell potential of the anode. Okay, so now we just need to plug our values in that we looked up in our chart. So to find the overall cell potential here, we plug in the value for the cathode. The value for the cathode is 1.33 volts, and that's a positive 1.33 volts. We subtract that from the cell potential of the anode, which is a positive 0.45 volts. So the way in which we solve for this particular problem here is we take 1.33 minus 0.45, and we get a value of 0.79, and that is a positive. And again, I like to put my positive sign here, so we have positive 0.79 volts. Okay, so again, key thing here with this, determine first what particular substance is oxidized, what particular substance is reduced. Remember, oxidation is associated with the anode, and the cathode is associated with the reduction. You look up those values in our standard reduction potential chart. You write them down as listed, and you keep that particular sign. And then once you have the anode cathode established with those standard cell potentials of each half cell, you plug this into the equation to get your values here. All right, so a lot's going on, but the key thing here, start out with identifying what substance is oxidized, what substance is reduced. All right, so let's keep going through some more examples here and keep moving on with this process. Okay, so with this particular process here, it kind of just throws you to the wolves. It says, hey, here are some reductions. They're both getting reduced. You're going cadmium 2 plus to solid cadmium and tin 2 plus to solid tin. And it says, hey, you need to determine what is being reduced, what is being oxidized, and then ultimately calculate the cell potential. So when we are given a situation like this, what we need to do first is we need to look up the standard cell potentials. So what I'm going to do here is I'm going to look for cadmium 2 plus on our charts. And so I will first look for cadmium 2 plus on this chart here. Okay, if we look closely here, I do not see cadmium 2 plus. So if it's not in this table 20.1, then we need to turn to our standard reduction table. This lists a lot more substances. It's a little bit more comprehensive. And so again, I'm looking for cadmium 2 plus, cadmium 2 plus. Oh, there it is. Cadmium 2 plus 2 electrons that yields solid cadmium gives a standard reduction potential of negative 0.403 volts. So I'm going to write this down. I'm going to say our E cell is equal to negative 0.403 volts. All right, that's great. Now I'm going to do the same thing for tin. Again, I'm just going to use my table from the periodic table packet. I'm looking for tin 2 plus to be reduced to solid tin. So I'm going to look down my line here. Again, I'm looking for SN 2 plus. I'm looking for SN 2 plus here. And got to keep searching. And down here at the bottom right, so tin 2 plus, SN 2 plus 2 electrons gets reduced to solid tin. It has a standard cell potential of negative 0.136 volts. So I'm going to write that down. Our standard cell potential here is negative 0.136 volts. All right. Well, okay, great. We wrote this down, but what does that mean? All right, so here is our key to success on these types of problems. The more positive the standard cell potential is, means that is the location of the cathode and the reduction half reaction. Okay, so let's take this into account of what this is actually saying here. All right, so we are looking for the more positive numbers. Now, these are both negative numbers, but the more positive number is this negative 0.136 volts. Well, what that means is that tin is going to get reduced. So that means we have 10 2 plus 2 electrons yields solid 10. Okay? And that right there has a standard cell potential of negative 0.136 volts. And I want to identify this here as our cathode because it is more positive. All right? Now, on the flip side, the more negative the E cell or the standard cell potential is, that is going to be our anode and the location at which the oxidation half reaction occurs. Okay, so I want to emphasize this. Oxidation, remember, is loss of electrons. So this is showing a reduction. So what we're going to need to do, because this is more negative, we're going to need to flip our products and reactions. So our oxidation would be solid cadmium gets reduced to cadmium 2 plus our 2 electrons. Now, over here, the bottom part here says the standard cell potential. What is the standard cell potential? Well, our formula stays the same where we have the standard cell potential of the overall reaction is equal to the cell potential of our cathode minus the cell potential of our anode. Okay, now we don't know the standard cell potential because that's what the question is asking there, but we do know the standard cell potential of the cathode, which was negative 0.136 volts. So negative 0.136 volts minus the standard cell potential of the anode, which I meant to label here. The more negative value in our standard cell potential is our anode. Okay, so our anode is a negative 0.403 volts. Okay, so remember, negative minus a negative is going to be a positive number, but I'll show you here. Negative 0.136 minus a negative 0.403. We press enter and we get a value here of 0.267 volts. So the cell potential here is our positive 0.267 volts. And again, if you think about this here, remember, this process of a voltaic cell has to be a spontaneous process, which means we should get a positive standard cell potential of the overall cell. Now, I want to go just a little bit further and show you the overall reaction. And so I'm going to write down our reduction half reaction. So I'm going to have 10 2 plus our 2 electrons yields solid 10. And then we're going to have cadmium, solid cadmium, gets oxidized to cadmium 2 plus our 2 electrons. Now, remember from our adding our half reactions, the overall reaction, which I'll write this down, overall reaction is as follows. The same thing on opposite sides of different equations cancel. So that means our electrons would cancel, and we would end up here with 10 2 plus solid cadmium yields solids 10 plus cadmium 2 plus. And this right here, I'm running out of room, this right here, this whole reaction would be given a standard cell potential equal to a positive 0.267 volts. Again, that is the overall reaction. Okay, so key things here is this. Write down exactly what you see in your standard cell potential or your standard reduction potential table. The more negative the value is the cathode, the more positive, or excuse me, I said that backwards. The more negative the value is the anode, the more positive the value is your cathode. This is key when you're given two reduction reactions like this. All right, one more concept and one more example here, and that's identifying what is the stronger oxidizing agent and the stronger reducing agent. All right, so we have some general rules to follow for finding the strengths of reducing and oxidizing agents. Okay, so the more positive the standard cell potential is, the stronger the oxidizing agent. The more negative, the stronger the reducing agent. Okay, and so we need to look at our half reactions here. Okay, so let's go ahead. We have some more steps we can go through and utilize, but let's go ahead and let's do an example. All right, so with this here, we have just a little bit more directions and guidance here, and it says at the top, predicting if one reactant can spontaneously oxidize another. Well, here is our key thing. The reactants of the half reaction at the top of the standard reduction table are the most readily reduced species in the table and are therefore the strongest oxidizing agents. Okay, so at our table, again, the top of the table, this is why this table is labeled the way in which it is. And it says, look, the stronger the oxidizing agents are located at the top. Now, on the flip side here is if something can reduce another substance. And it says the products of the half reactions at the bottom of the standard reduction table are most readily oxidized species in the table and therefore are the strongest. Okay, and so I want to show you this table here from our notes. Again, more positive means stronger oxidizing agents. More negative means stronger reducing agents. Again, use this table. I pulled the wrong table out. Use table 20.1 for these purposes. Okay, and I'm gonna label that here. Use table 20.1 for these purposes. Okay, so I'm going to use table 20.1, and it says, hey, using the standard reduction table, rank the following ions in order of increasing strength as oxidizing agents. So the first thing that I'm going to do is I'm just going to list each of these particular substances. So I'm going to have NO3 minus, and I am going to just leave it blank. We'll look that up here in a second. I'm going to have silver ion, so Ag plus as our aqueous here. And then we'll have our chromate, dichromate, and we'll look these values up. Again, all I'm going to do is look for each of these substances here. Okay, so on this particular chart here, I find NO3 1 minus. We see here it has a value of positive 0.096. So I'm going to put a positive 0.096 or 0.96. I turn my table again. I find silver has a value of 0.80. Okay, again, positive 1.80 volts. And then I turn my dichromate. My dichromate has a value of 1.33 volts. Now, if you want to look back on the previous page of notes, we have this. The more positive the standard cell potential is, the stronger the oxidizing agents. So that means we need to go from lowest cell potential to highest. I'm going to write that down, pause and write that down. All right, so there it is. For this problem, because it wants increasing order of oxidizing agents, we're going to go from smallest to largest. So that means the smallest value is that of silver. So silver here would be the weakest oxidizing agents. The next highest number here is our nitrate, our NO3 1-, and then our strongest oxidizing agent would be that dichromate. Okay, and I just want to label these as follows. For this particular problem, this is the weakest oxidizing agent. And over here on the right, the dichromate is the strongest oxidizing agent. Okay, so we've done a lot in this particular section. The key thing to remember here is identifying what substance is oxidized and what is reduced. That allows us to identify the cathode and anode respectively. And then once you identify that, all you need to do is look up those standard cell potentials in that standard reduction table that is provided and plug that into your formula, where you take the cell potential of the cathode minus the cell potential of the anode, and that's how you get the standard cell potential of our oxidation reduction reaction. And then remember, our standard cell potential impacts, is something stronger oxidizing agent or a stronger reducing agent, and that's how we rank our substances. The key thing here is to utilize your standard reduction table charts and find those values. Make sure you utilize those values in those particular tables. All right, I hope you have enjoyed this particular episode, and if you haven't done so already, make sure you subscribe.